recording.
Cool.
And the stage is yours.
Thank you very much for the introduction. So the topic of our presentation is real-time stream analytics and scoring using Apache Flink, Druid, and Cassandra. During this presentation, I'd like to introduce key challenges that we try to solve using our platform. We will be discussing the design choices we made and what obstacles we faced in the process of building a data pipeline. I know that on the previous meetups, frameworks such as Apache Druid and Apache Kafka were demonstrated and discussed. That's why and I also know that Apache Flink was not one of those frameworks that were mentioned. That's why I will also spend few slides on Flink, on details how it works and when it can be used, and in general overview of the framework. Okay, so first, who we are. My name is Michał, and I'm head of AI at Deeb.BI. I'm a software engineer, data scientist, and system architect. And with me is Sebastian, who is our CTO.
Hello.
He's also a software engineer, data scientist, and system architect. Copy paste. Oh, sorry.
Yes. Got a mistake. We are just sharing the same background here.
Okay, so what does Deeb.BI do? In short, it provides scalable end-to-end AI solution. So we collect and process billions of events daily to track user habits, engagement, products, and content performance in order to optimize target key performance indicators. Key problems we try to solve is, we mentioned here, customer acquisition, product usage, user retention, churn, and fraud detection, compliance monitoring, and so on. Our customers come from various industries such as media, marketing, retail, restaurants, insurance, pharma, and health. And maybe let's introduce some numbers here. In total, we've processed around 2 petabytes of data. It's around 40 billion data rows processed per month. We score about 100 million users each month, and at peak hours, we process around 100,000 events per second. This also, we can also state that we generate around billion AI predictions per month. What's also important, all of those numbers, all of those events are processed with less than 1 second latency. So it's not only big data, but it's also real time. Some example use cases. So in general, our goal is to provide real-time insights based on really custom metrics from a variety of self-created dimensions. You can connect any data source, any data structure, and the platform allows you to perform different tasks from various domains, such as adjusting websites using real-time analytics, running AI-driven marketing campaigns, providing personalized user experience based on user profiling and AI scoring, or detecting frauds or compliance issues based on data analysis and adaptive patterns. I've also said that we do applied AI at scale. One may ask, why is that really that important? I will try to answer this question by providing an example of one of our products. It's called Propensity to subscribe. And usually when our client comes in, he already knows what features in the data are important to recognize certain patterns. For example, usually we know that the more a certain specific user is engaged with a product, the more likely he is to buy, he is to purchase it, right? Or to subscribe, whatever, purchase of something. And also, usually, it's not very difficult to visualize such an event flow driving to conversion, just like on the chart above, on the red one, right? So here we can see that the red plot shows the user engagement, and the more engaged he is, the more likely he is to convert, either it's purchase a product or a subscription. The problem here is it's actually hard to detect the exact moment of this conversion. We don't want to spam the user with notification. We don't want to block any of our features when it's too soon. We want to easily identify the right moment to perform specific marketing actions. And here, such an AI modeling comes with help, because such a score, AI-driven score in real time, enables you to spot the exact moment at which you should apply some kind of treatment to the user. Such a model takes all available metrics and transforms it into a single score representing this propensity. And using that, you can automate your marketing actions, for example. Okay, interestingly, as artificial intelligence has been a hot topic for a while, there are still only a few cases where it's applied to real world in production and large scale application. The thing is that the reality does not look like a Kaggle competition. In many sectors, companies lack experience in applied AI. They hire few data scientists who build models, but they rarely work on production. In real world, your problem is not a competition. You actually don't know how your target is exactly defined, specified. You usually don't have all the data at your hand. You have to collect it somehow, process it, clean it up, and afterwards you need to deploy the solution in production and monitor it, right? So if you're talking about applied AI at scale, it's not only about data science. It's not only about AI tools. It's a lot more. You need to, as I said, you need to define the business requirements, build a data collection pipeline, storage layer, orchestration, deployment, monitoring. So if you want to build an end-to-end solution, you need to combine all of those technologies, all of those things together in order to build a solution that works and is useful. This is the reason why even more mature companies who employ hundreds of data scientists suffer from so-called POC syndrome. For example, one of the largest pharmaceutical companies in the world that employs around 300 data scientists. Sorry, my bad. So a company, one of the biggest companies, pharmaceutical companies in the world, out of 300 data science projects that are that are working on there, out of those 300, less than 2 work in a production environment. So only even less than 1 in 10, right? Why is that? The problem is that creating an AI model is just 10% of the work needed to build a complete AI-powered system. In order to build and accomplish these tasks at Deeb.BI, we built an architecture that can handle it. Our system collects, maybe there's a pointer here. Yeah. So our system collects every event through an ingestion service. So you can push the data there, it can pull the data, multiple connectors available, and everything is pushed to a data streaming platform. Here we use Kafka. Subsequently, the data stream on Kafka is enriched using Flink. We use external databases to enrich the data, enrich events. We transform the data, so we do ETL on streams in a streaming manner. We score events, users, items on the fly, and also we add features to the data. Then the data lands back on Kafka and serves multiple purposes. The processed data is indexed by Apache Druid. In real time, it's basically for real-time analytics. And also the same data is pushed to Cassandra for score delivery. So basically, if you want to score specific users that have an ID, we use Cassandra, and those scores are always available there. Historical data is also stored in Hadoop for machine learning and model building. So from here, the data is collected to model training frameworks such as Apache Spark or TensorFlow. The models are prepared, and finally they are deployed back on Flink. So again, on our stream processing engine. And everything is available through a specific API. So we do have an analytics API, a prediction API, model serving API, and so on. And underneath, we have built a system orchestration and monitoring using solutions such as Kubernetes, Zookeeper, Grafana, Prometheus, and so on. So that was quite a complicated diagram. I will try to focus on less components on this one. So here we have an AI, how a data flow, how a data pipeline looks, an AI data pipeline looks at Deeb.BI. As I said before, we have an ingestion service that its only task is just to collect the data and push to Kafka. Then everything is processed in real time, mostly on Flink. So here again, we do enrichment using external data sources, AI predictions, user profiling, and so on. We also have other Flink jobs that serve different purposes. I'll just talk about it in a minute. And we have different APIs to access the data. Focusing on parts of the system, we can separate, can distinguish a learning pipeline here. So here, the data is ingested in the same way as for real-time analytics. Data is processed in real time and available right now. Afterwards, we do some so-called event attribution. This additional step is required because not all of the information is available at this specific moment. This is mostly when we want to build an AI model that predicts whether someone is interested in a product and purchases it. We need to generate predictions not at the moment of purchase, but before, right? So that's why during learning, we also need to know what kind of actions or products or product views led to specific target actions, such as purchase, right? So by event attribution, I mean all of those events that led to desired action are just attributed with additional information. So we use some kind of window aggregations here. Data lands on Hadoop, mostly on Parquet, and it's used for building models. We use different technologies for that. It's Apache Spark and TensorFlow. We also use Kubernetes to orchestrate some of the pipelines. Models are trained periodically in an automated manner. But the good thing is that they always have the most recent data as possible. And finally, the serialized model are delivered back to the real-time pipeline so that it can be used for stream enrichment. Similar components are reused for scoring. So here again, we use the same ingestion and the same enrichment process to score users. So the model, the user profile, everything is stored on Apache Flink, and each event is scored and pushed back to scoring, pushed further to scoring API, and it's available for querying. Same components are also used to for analytical processing. For this, we use, as I mentioned before, we use Druid. Here, also, this real-time enrichment are helpful because some queries are hard to be processed in real time, and by enriching the data in a specific way, we are able to prepare really complicated means of accessing and querying the data. And last step, what's also very important, is monitoring. Here, so the same data that we used for training, we also push to a metric monitoring job. Basically, we define metrics on Flink that just collect the attributed events. Model predictions are also available here, and we can compute those metrics in real time, and again, push them back to Druid. So using such a pipeline, we can basically build components that are reused everywhere. So when we define features for machine learning, they are defined once and available for different purposes, for analytics, scoring, and model training. There is no need to re-implement some parts of the system. Everything is done as implemented in one place. Okay, so you've seen that we use Flink a lot. Probably not all of you know what Flink is. So in short description, it's a framework for scalable, stateful stream processing. Its key features are low latency, high throughput, high availability, and flexible API. And all of those were important for us when we selected the toolkit for building our platform. So what those features mean exactly? Scalability. So by scalability, we mean here distributed processing. The same job, the same code implementation may be easily distributed by unlimited, basically, number of workers. Just need to define the parallelism of your job, and it will be distributed evenly across the cluster. It's quite easy in case of stateless transformations. Like there are dozens of frameworks that are able to do that. It's a bit more hard if you do stateful computation, because the events has to be routed in a specific manner. The state has to be distributed properly across the cluster. And Flink has two options here. It may store the events either in memory or on disk using RocksDB backend. It's basically a distributed internal key value store. As I mentioned, Flink, most important is Flink is state. It supports there is a support for very large state. By large, I just mean larger than total memory of your workers. It enables low latency access. So usually when you do stateful computation, you are required to access some external database, for example, which is problematic because it usually lowers the throughput and increases the latency. By having everything in one place, we can make some parts of our system easier. Also, by making state as an internal component of Flink, we can guarantee exactly one's state consistency, which is not possible if we use external, or at least very complicated in case of external systems. What is also important, in most cases, and when we talk about Flink, we talk about unbounded streams. So our data streams don't have an exact end. Those jobs may be running for years. So it's important to keep the size of the state manageable, and to do it, there's a time to live feature for values stored in the state, which is also important. So Flink actually has two ways of processing the data. Currently, it's in the future, they both will be unified into a single interface API. But right now, there's a batch API and a streaming API, but the batch one is actually on Flink just treated as a special case of streaming. So basically, a batch is just a bounded stream. It has a beginning and it has the end. And when you're doing batch processing, you can apply some optimization that you cannot do when you're streaming live data. Flink comes in with built-in operators such as window aggregations, late event handling, custom timers, and so on that you can use even using SQL queries, so without any special coding. Okay, so we know that Flink is quite a versatile framework. Enables you to scale, process the data fast. But those are not the only reasons why we've chosen it. Basically, all data sources Deeb.BI are data stream. Whatever the endpoint, through whatever endpoint the data is pushed or pulled, everything basically lands in Kafka and is processed as a stream. And in our case, usually the stream processing is treating pipelines as data streams, streaming data flows. It's a lot easier than doing batch processing. One of the key factors here is that stream processing is event-driven. So we define event-driven application, which basically enables you scalability. You can scale your workload easily across multiple nodes. When you have a traditional transactional application, it's at least a lot more complicated. You have to scale multiple components. Some of them are really hard to scale. What's also worth mentioning is that the data comes as already ordered. This is a very nice feature that you don't have when you process batch data. Of course, you can always sort the data, but if we are talking about big data, so data that doesn't fit or cannot be processed by a single thread, basically, it's impossible to sort the data to match multiple different partition requirements. Sometimes we want to sort the data. So whenever you sort distributed data, you always has to specify a partition key. So because the only sort order that you can guarantee is on the partition. So if you need that data to be sorted by users, by items, you probably will end up with having to sort the data multiple times. This is not an issue in real-time processing because the data is processed as soon as it's available. Also, having a continuously running data pipeline makes management a lot easier. Just running all the time is deployed and just process the events all the time. You don't need to set up some scheduled triggers to start your application to process the data all over again. Okay, so we used Flink to build a data streaming solution for us. we try to build feature engineering frameworks that provides reusable templates for data enrichment. We are able to define the logic using a separate control stream. This enables us to change the business logic at runtime without the need of deployment. Also, the framework enables us to serve machine learning models. So our solution was built using a low-level data stream API that Flink enables. We use custom process function and broadcasted state. And this allowed us basically to define domain-specific features for analytics and machine learning, and to migrate our batch data processing pipeline from Python deployed on Apache Spark to Flink, which resulted in a significant performance boost, but also made the maintenance a lot easier. And on the following slide, I would like to focus on some of the challenges that we faced during building our solution. So at the beginning, we wanted to build a feature engineering framework for everyone. In general, implementing streaming pipelines is difficult. Deploying them is not that easy as writing few lines of code. For example, for data scientists that don't have experience, sometimes don't even know the programming languages used here. For example, to write, at least right now, to write a streaming job on Flink, Scala or Java knowledge is required. So that's why we wanted to build a solution that will enable developers and data scientists to define features without knowing Apache Flink at all. So just try to build a layer on top of Flink. What was also required here is the ability to separate unit testing of the features. Just so that we could employ good practices by testing before deployment, which was not always the case in our previous data science pipelines. When we talk about stateful stream processing, performance depends a lot on the size of the state, which can grow large. In the worst case, for example, we can imagine that we could store all events on Flink that we've received. This would make this state enormous and unmanageable. That's why we wanted to implement all useful features that would enable our users to just reuse those predefined patterns to build features that does not require accumulating large states.
Sorry, may I ask
yeah.
a question? Does Flink use core Java or Scala or something other JVM?
So Flink is implemented in Java, but there is a Scala API available. So we implement most of our pipelines on Flink in Scala. There is also a framework called PyFlink. So it's similar to PySpark, but as for now, not all of the Flink features are available. basically this low-level API is only available in Java Scala, and there's also, so this is the streaming API that we use. There is also a so-called table API that enables you to connect different sources and define SQL queries on top of those. And for this, you can also use Python. It's not only about SQL, but it's about implementing UDFs in Python. So actually, you can use pandas and even deploy machine learning models in Python on Flink.
Okay, thank you.
Also interesting here, if I may add, because you may be wondering how the Flink is different from Spark and why we've chosen Flink. And Michał mentioned many times the Flink state, which is, I think, one of the coolest things here. And let's imagine that, for example, we need to calculate features for like millions of users, and we have their raw events. So on Spark, we would need to get all the data, group it by users, sort it by time, and then calculate like time-related features. And it's more like batch process. On Flink, we can keep this, so we can calculate the features on the fly as new events arrive. So you can keep the state, like the really large state, like gigabytes of data, or even there is a known case at Alibaba. Their state is over 1 terabyte. So you can keep the state and keep the features, and as events coming in, you can update them on the fly. And this is one of the major advantages here.
Yeah, especially compared to batch processing. Probably some of you know that there is something called Spark streaming, or there are also different streaming frameworks, stream processing frameworks. But as Sebastian mentioned, the key feature there is ability to keep the state, to have the state bigger than your memory. This is not possible on Spark. You either have to build a framework yourself, or use external data sources, which is really complicated, especially in cases of, for example, failure recovery, or when you want to reprocess something, right? On Flink, this is also very important there, that you can save the state of your job that is currently running and resume it afterwards. You can also do some kind of A/B testing, right? You can have one job that is running, you can save the current state, it's called the save point, and run 2 jobs and compare the results. This is very handy. Using external state storage, this would be really complicated because you'd have to have a versioned storage, which in those high performance scenarios, low latency, would be hard to achieve, let's say. Also, why build something like this on top of Flink? If it's even so, Flink, for example, supports SQL, right? You can define a SQL query over your data stream. Why not? Why build a framework that itself is probably complicated, right? Instead of using SQL queries. The problem here is that in most cases, you would probably end up with multiple SQL queries. This would mean that you need multiple jobs running on your cluster. If you had like 200 features that you want to enrich the data with, would require like multiple nodes of your cluster, multiple jobs deployed. This would also be, this increases the maintenance cost. And building a feature engineering framework inside of Flink, we can actually have a single process that enriches the data. And it's also a lot harder to break something, which is also a very nice feature because it enables people to experiment with the data.
Okay, we have one more question.
Yeah.
Can we use Spark structured streaming in place of Apache Flink?
Well, it depends on your application, because in some cases it might be even better. So because Spark streaming enables you to write pipelines fully in Python using lower level API, so not just SQL. And sometimes there are different connectors already available for Flink and for Spark. So if there's no connector for Flink and there's a connector available for Spark, then you may be better off with Spark. I don't know if there's such a case, but maybe there is. But in all other cases, probably you'd be better off with Flink. Why? Because if you, I'm assuming you want to do stateful computation. State management on Flink is built in. It can handle terabytes of state distributed over multiple hundreds, probably nodes, cluster nodes. So if you want to store large state in your application, Flink probably will give you better performance. Spark just stores data in memory, or you would have to have a separate database. Also, the API of Flink is provides you more built-in features compared to Apache Spark. I would rather compare it to Apache Beam because this is more similar in terms of functionality. I think this covers it. So going back to the slide, so basically how our feature engineering framework was designed. On the left, we have our event stream. So events are processed by the application. For every event, we extract information that is required. And we use this information either to build a feature value, or to reduce this information with the information extracted from previous features, and build a feature based on that. I have a code example, simple one actually. So this is how you could define a simple counting feature using the framework. So you basically have to define three functions, sorry. So extract, reduce, and build. Our count function just needs to count events. So we just extract, sorry, constant value from events. Reduce function just adds them together, and the build function actually just returns the accumulated value. So we accumulate each event as one. We join them together using just arithmetic sum, and to access it, we just read it, the value there, right? So this is a very simple function, but you can imagine that you can build really sophisticated features there. Of course, you don't have to define so simple features in the framework, because there is a lot of built-in functions. Simple ones such as count or average are of course available, but also more complicated ones like sliding windows, approximating counts, or top and frequent values, and so on. So it's one thing to enable the developers to easily define the functions, the features that are either required for analytics or machine learning. But what's also important is the ability to dynamically update the pipeline. So this was also one of our requirements. It's just the need to update the business logic at runtime. So without the need to redeploy the job. So usually when you want to update your code base that is running in production, you just push the latest code, redeploy the job on Flink, and it can be processed. But there's another option to do it. You can actually push the data to containing some feature definitions, controls to a separate stream. So in our Flink application, there's always an event stream with the data that is processed in a real-time manner. And there's also a control stream that contains definitions of features, functionalities, transformations. And this control stream is, of course, a lot smaller than the event stream, and it's broadcasted over all Flink operators or all Flink workers. So basically each worker, each node contains a copy of the feature. And this simplifies the deployment of new features because the only thing that you basically need to do is just push the definition to the control stream. So what is important here is just to find a way how to version it so that you can know what exactly happened and how the data was processed. So in our framework, we support multiple different ways of defining features. All of our events are serialized as JSONs. So because this is just unstructured data, there's no schema there. That's why one of our first features was the ability to query whatever field we want. So we use JSON path for that. Since our data is JSON, we also have the ability to define transformations in JavaScript, which is very handy in case of JSONs. But there are also other different ways of defining features. For example, you can implement functions in Python. There's a custom format called portable format for analytics, and multiple others. One of them is, for example, TensorFlow graphs that you can serialize, Spark models, CatBoost models, and so on. So basically, when we want to deploy a a machine learning model, you just need to serialize it and push to a specific control stream. Oh, demo. So I wanted to show you how it works. I'll just switch my application. Give me a second. Or maybe, do you have any questions? Are there any? No. So let's move.
May I ask?
Yeah.
Maybe.
Yeah, of course.
I wanted to ask about your machine learning, because this Flink can stream data based on events. So possibly you have machine learning model running testing, validation, etc. So every event is written to this machine learning, or this is in batches or something?
So every event is pushed there. We actually have a process called an event attribution that can have some filters or aggregations. We actually don't need all of the events in all cases. It's not a problem, but we can also filter them just before learning. Maybe it's not even just before learning, because we always do that, but just before pushing them to a durable storage, not durable storage, pushing them to data lake.
But the model is learning in real time, right?
No, actually, no. The models are trained in batch, so we don't do online learning. Usually, we update the models on a monthly basis. So there is just a process that does the same operations all over again. The data is available under the same path. It just picks up the data, runs the trains the model, runs cross-validation, hyperparameter optimization, compares, evaluates, produces all the metrics, compares with the previous algorithm, and generates a report. And then we can decide whether do you want to deploy it or not.
Okay, thank you.
It is possible to actually do it in real time on online learning. At least in our cases, it was not that important, at least from the performance perspective. And it's a bit harder to monitor the performance, right? Having a batch process, it's possible to validate before deployment, right? If you do online learning, something might go wrong. Of course, you can monitor that, right? But what if you receive the confirmation about successful conversions, not after 5 minutes, but let's say you're trying to predict whether a customer will churn, and you will receive confirmation whether an algorithm works after 2 weeks or a month, right? This is hard to manage in real time, and usually not necessary.
Yeah, I agree.
Okay, so let's try to do the demo. I've prepared, I wanted to show you our dashboard.
I wanted to mention one thing.
Yeah.
So, what is interesting in our data science pipelines, so as Michał said, we train models offline, but when we build pipelines, so we use like unified pipeline for building features for training and for prediction. So we use Flink for feature engineering, and so as the model is trained and tested, in fact, it's ready, to be deployed immediately. So because we have all of the transformations that will happen on production environment ready to use, ready to deploy. So it's like online feature engineering and online transformations done in batch, like in batch training, but ready to be run in this streaming manner. So this is I think still quite unique here. So we don't have to like redevelop Jupyter notebooks and all of this custom Python stuff that is notebooks, because we have this data transformation feature engineering part done on Flink. So we can run the model plus the pipeline like right away.
Yeah, and
I see.
And actually your patterns, right? You train the model to detect some kind of patterns, right? And usually your patterns don't change every second or every few seconds, right? In some cases, like this model can be even constant, right? If you have good data, you could just train the model and forget. The thing that changes is your data, right? Your user changes, your data shifts in different ways. That's why you need those features to be computed at real time. That's why you need those predictions to be available at real time. But because this changes every few seconds, basically, or even faster. Someone makes an action and suddenly predictions for him will change a lot. But this doesn't change the basic patterns and the data.
Yeah.
Okay, do you see the dashboard right now?
Yes.
Yeah, we see.
Cool. Okay, so this is actually a real-time. So this is our panel that uses Apache Druid underneath. So quick introductions for that. So it queries real-time data. So I can actually show you. So for today we have, this is a small data source used for development. So for today we had like around 1 million events. We can also view it on a line chart. So how many events were processed. We can also enable real-time verification. You can check how many events we had last minute, and you can see that last minute we have around 1,000 events and split by, and you can also view this on the line chart here. Okay, so this is fairly easy, and what I wanted to show you is just how we can, and so this everything that I'm showing you is the data is collected on a website. It doesn't really matter which one. Goes through our ingestion API, lands in Kafka, enriched on Flink, then is pushed back to Kafka, indexed by Druid, and then you can query it using this panel. What I wanted to show you is how to push additional transformations to our data stream. So that's why I wanted to define 2 features. Let's say we want to split our users into groups for A/B testing, right? So here we have a simple metric. It's just the count of all events that are available. And let's say we want to count all number of events that are marked with group A, and count the number of events that are marked with group B. So we will have a user group defined somewhere, and in one case it will be A, and in the other it will be B. So we have 3 metrics now, A, count over all events, and count filter by group A and group B. This can be used, for example, for A/B testing. I will add these counters here. Maybe this way. And they should show me 0 because there is no events marked with those with this data. I can also add them to the line chart. And it should also show zeros, right? Now, so we've prepared our dashboard. Now let's try, I can save it. Yeah. Now let's try to define a feature. I will do it on everything and on one window in command line console, so that we don't have to switch. You can actually we usually use an IDE for that, but those will be simple features. So not difficult coding here. So I've prepared a simple feature called a user group. It's defined in Python. I can show you how it basically is defined. So basically, we compute a hash over a specific value. If the hash is non-zero, it will return A, and otherwise it will return B. So very simple function. Just will split basically the data in half, right? Because this is a modulo, and it will either return 0 or 1, right? When it will be 1, it will be A, and 0, it will be B. And also for our function, we need to define some kind of metadata. I've also prepared that. And here we just need to define what kind of variables and the data that we use. So here I wanted to use a user ID. And just it. So this value is extracted from the JSON, and then we can use it in our function. Now what we need to do is just to put push this value to a specific control stream. I will use our development environment here, specific user that we've created from the demonstration, and just push this specific feature called user group. This Python function will be validated and will be pushed to a control stream. And it should be done. And let's go back to our application. And we see that something changed, right? Just seconds ago. You can see that that events marked with group A and group B started appearing. Of course, they should be more or less equal over time. Of course, the longer you will observe it, they should level up. Should be more or less even. Okay, so
so Michał mentioned it, but I want to reinforce this. So what we've done is we have changed live stream of data without stopping any job, even there was no redeployments, like anything. We just applied new logic to the live stream by just uploading this logic to so-called control stream. So those two streams now merge. So control stream applies this dynamic logic to event stream. It's cool for like transformations, but also, for example, like here A/B testing. So for example, you may have in one control stream you may have features. In the second one, you may have a logic, that splits data, for like A/B testing. On the third one, you may have a model that can be also deployed in the control stream, and the model logic is applied live on this stream of data. So this is really cool in terms of testing and flexibility when you have this live stream data.
And it's also very simple to modify this logic, right? Because the only thing that we need to do here is just to update our definition. For example, we don't want 50-50 split. We, for example, want one event to go into one group and 9 to other, or whatever split we want. Just push it again. It will be just parsed and pushed again, pushed to the control stream, and should be after this. It should be just available for querying, right? So I've changed the let's look at now, right? I've changed the definition of my feature. Group B should be like 10% and group A around 90%. So we can very easily modify any events. What's also important, those feature definitions may depend on each other. So as Sebastian mentioned, you can have like this A/B test definition defined somewhere, and then you can have different machine learning models, and depending on the group to which user is assigned, you can use a different model. I've also prepared a model for this demo. Probably this is a bit less interesting for viewing, but I think it's somewhere. Yeah, there's a model. It's just like some kind of binarized data. So basically, there is it's just a serialized model that we can deploy over our data stream just in the same manner as previously. We just need to provide the name of the feature and push it to the control stream. Here again, the feature definition will be picked up. Oh, something is wrong. And if something is wrong, you will get a notification. So I probably made a mistake, but I will just fix it. Right now it's telling me that the name of my feature does not correspond to the name of my file. Actually, I can fix it. Let's fix it. So there's a control message for this specific model. It's basically there's a name that is different from what the application did expect. I can just remove it. Just a sanity check. So it's actually very important to validate. I made a mistake. To validate your data. I broke something, sorry. Unknown token age. Oh. This is what happens when you do live coding. Sorry for that. But in general, what you can, so it's better to use an ID instead of using a console for that. Why is it? So I'm sorry because I probably messed something. It actually means that my machine learning model cannot be pushed because it's invalid. So this basically it tells me that this message that I just showed you before has an error somewhere, and this was not properly serialized, which is quite troublesome for me. I will try to replace it with something different. I'm not sure if it takes me more than I should probably drop it. Do you have any questions in the meantime?
I remember something about Cassandra in your architecture, and there was something about scoring. Could you elaborate?
Yes. So we basically we push the events to Cassandra because every event is enriched on Flink. We can just push it to Cassandra, and when we query it, we just need to provide a user ID, and we will get all the attributes that correspond to the specific user ID. Right. So if you want to have, so Cassandra is a key value store. So just pushing the most recent value there makes the latest predictions available for querying. This is very handy because it's usually a good practice to separate ingestion from querying. You don't want any kind of failure that occurs in the ingestion affect your querying abilities, right? Querying should be always available and should be always ready to return some kind of results. And we just use Cassandra for that. So yeah,
Cassandra it's like super fast when you would retrieve a single record, like for example user profile. So you query a user ID and you get user profile on here. If you ask about scoring, so we call all of our predictions user scoring. So we score users against their propensity to subscribe, propensity to churn, propensity to register. So we calculate those scores in real time. So we make predictions real time on Flink, and we push the scores with user IDs to Cassandra. So our scoring API, as we call it, or prediction API, can retrieve a single user profile in like under 50 milliseconds, where Cassandra's part is like 5 milliseconds. So the rest is communication, HTTP, etc. So Cassandra is our component that can handle this massive, real-time querying for user scores. So yeah, and so we keep them calculated things previously on Flink, and then we don't query Flink, we query Cassandra for this.
And also Cassandra is very good in this because the data is replicated over multiple nodes. So if one node fails, the data is still available for querying without any stops. In terms of Flink, when one node of the cluster fails on which the job is running, what actually happens is just the job restarts. So basically, the job has to stop and get back to the latest known consistent state and start processing from then, resume processing from the last committed state. Usually those checkpoints are made every few seconds, so it's not a problem, but it makes the application not available for some time, right? Sometimes seconds, sometimes it may be even minutes. So this is not very, so it might be problematic if you want data to be available all the time. So sorry again, I think I've managed to push the model. I just had a malformed file with serialized model. I just replaced it with something else. Let's try to query it. ML model and search if our model is available. What we can do is for example, see what's the average prediction for each of the user groups. For that, we can just calculate the sum over all events that contain our model predictions divided by the number of events to get the average. So if you know Druid, you know that this query is, you can define such a query, but having such a tool simplifies the job a lot, right? So you can actually see, you can actually get the underlying query, but let's call it prediction. But using this web dashboard enables you to build those queries faster. And maybe let's split our data by user group. User group demo. And let's try to show it. And there's our prediction. Can also add the number of events in there. Yeah. So maybe not very no fireworks here, but in general, there is a machine learning model. Here is a propensity to convert model. Basically, it tries to estimate the likelihood of a user to convert. We don't have much users here, so basically there are just few events that are scored, but those predictions are made in real time. And we can actually modify those predictions. For example, let's say we have different models for different user groups. I'll try to show the last thing on this demo. So actually there's
also, if we could split by user and sort by prediction, it can be interesting to see like the most probable users to convert. So I'm not sure if this is possible in this data set. I think it should be. So
yeah, it's actually possible. So I'll show it in a moment. What I also wanted to show you that you can actually rely on different features in your data. So actually, this model is our two functions. One is a simple JavaScript function that just extract the prediction value from model output, and the other one is serialized model. And this serialized one was the one that was problematic. And we can actually add a condition here. Let's say we'll just check if our user group is equal to A, then we'll just return model prediction, and otherwise we will return model prediction, let's say times -2. So that those values there should be different. I think it should be fine. You can push the definition. Again, it should be verified if it's correct. I think it is. The definition was pushed. And now we should see different values in one of our models, right? So I've changed the model results for group B. And of course, I've multiplied it by -2, right? So those are 2 times higher with a minus. And also, as Sebastian mentioned, we can split the data by any attribute. This is a Druid function. So we have a user ID here. So we can split it by user. We can also split the model by some kind of user features. Let's say engagement. Let's say we will check the user segment. Maybe shorten name, user ID. So we can view it in panel on dashboard. For example, which user has the highest propensity. Just we need to split the data by user ID, sorted by prediction, and voila. Right, so we will have user sorted by the prediction value. We can also modify that and, for example, check how does prediction differ for based on user segments. So, for example, we have new users there, some kind of that are highly engaged users, and this is an actual model. So that's why engaged users have higher predictions, and new users are the less likely to subscribe. Okay, so that summarize our live demo. Let's go back to our presentation. Live demo. Yeah. Okay, so this was also one of our requirements, is machine learning model serving. How to do it with low latency? We just embed models into the data pipeline. So we just serialize the model and push it in the same manner as simple transformation as I just showed you. So we basically reuse the same enrichment pipeline that we use for data preprocessing. We use the same pipeline for model serving. So in the same manner, so again, all of the features, user features, are computed in real time. The models are retrained in a batch manner, so periodically, but the predictions are made also in real time in the same manner, and both like one can depend on each other. Few more slides left. I think we have like 5 minutes more, so let's
yeah, that will be good because we're running out of time. We have some
do we have 5 minutes?
Yeah, cool. That's okay.
Yeah, just I think 3 or 2 slides. So what's also important is job evolution. So when we are talking about unbounded data streams, and Flink jobs, we are usually talking about processes that are running for months or even years. At Deeb.BI, we have even processes that process the data for multiple years and still are processing the data. So fortunately, Flink enables options to migrate, like to upgrade our applications. There are a few options there. You can, of course, reprocess all the data and reindex it, but this is quite hard if you if your job is running for a few years, because it would involve like processing terabytes of data. You can also migrate the state. There's a function and thing that you can actually access the state in a separate process and modify it however you want. And finally, what you can do is actually you can replace the state on site, and that is actually running. We actually do it without any stop of data processing. So it's implemented such a way that we have an application that is processing the data right now. We make a save point of this application, and we start running it in parallel to the first one. So we have 2 jobs that are running in parallel, processing. So the application B is the newer one, and application 1 is the old one, right? Only the one of them produces output, and the other one just processes the data. And what we need to do now is just tell the application A to stop processing at some specific, stop producing output at specific timestamp, and say the application B to start processing, start producing output at the same exact timestamp. This can also be handled using a control stream. So again, without the need of redeploy, without stopping data processing, we can update the application logic. So there is zero milliseconds of delay in data processing. This is actually handy if you have like gigabytes or sometimes even terabytes of data. Stopping the application can take minutes. Without it, with using such an approach, it's not actually required. Maintenance, this is also important. You need to monitor your pipeline. Sometimes something fails. Flink has some features built in, but we also implemented some scripts for automated deployment, self-pointing, and upgrading our applications instead of manual operations. Yeah, and that's basically it. Wanted to give you a few takeaways from the presentation. So first of all, to run large AI systems on production, you need a wide set of skills. So it's not just data science skills that you need if you want to run AI models, but a lot more, right? You need data engineers, DevOps, and so on. And also when you need to specify the requirements, you need also people that are skilled in that. We found out that it's also better to have interdisciplinary teams instead of organizational silos. So basically, we want to empower people to use different tools instead of and to work together on a product instead of like have completely separated processes that each of them has their own separate goals that don't match the final product goals. Also, treating everything as a stream makes things easier. It's a lot easier to process the data when you just treat it as a data stream. We at Deeb.BI also treat batch processing as a special case of streaming. You can apply some optimization there if your data stream is bounded, which is fine. For example, sometimes you need to process the data multiple times for machine learning, right? So you need to shuffle the data for machine learning. But this is also just a special case. And I think this is quite important because we highly recommend building production-ready pipelines from day one of your project. This makes the deployment and the operation quite trivial, right? If you build your product with production-ready mindset, the deployment will be just easy. You can just, for example, to deploy a model, you just need to push a message to a control stream. And finally, it's worth creating reusable pipeline components that reduces the cost. So this was one of our motivations to build our feature engineering framework, because we could reuse most of the codes for feature engineering from project to project. So at Deeb.BI we have like tens of AI projects, and all like 90% of them at least use the same code base to build the features. So this is very handy because when you implement a single feature, then it can be reused and in all future projects. And thank you for listening. It was a bit longer than expected, but I think we've managed in time. So please contact if you want to discuss or need more information. Our emails are here. Do you have any questions?
Thank you so much. It's for me, I'm the Kafka administrator, and it's super interested. So once again, thanks for your time, the great presentation. And I think that's the time for the questions. So please use the button, raise a hand if you have any questions, but I'm a little bit privileged, so I will take this opportunity.